This reaction right here is known as the Wolff-Kishner reaction or the Wolff-Kishner reduction because it reduces ketones and aldehydes to alkanes. And where it is really shines is reducing acyl benzenes like this right here, where you can imagine we did a Friedel Crafts acylation, and then reducing it to the corresponding n-alkylated benzene. And this is really important because we can't achieve this n-alkylated benzene directly through Friedel Crafts alkylation. If you remember, there is a carbocation intermediate there, so we'd have a rearrangement. We'd not get this product right here. So what we do is we can make the acylated version and then use this Wolff-Kishner reduction to reduce it down to the alkane that we actually really wanted. Now, there are other ways of reducing. There is the Clemmensen reduction, which is acidic, but the one we're going to cover is Wolff-Kishner, and it is a basic style, or it is basic, under basic conditions, reduction. In the first step, we use hydrazine. The second step, we use a strong base, commonly IC, potassium hydroxide, and then we need a high boiling point solvent because this does have heat, and I'm forgetting heat. Okay, so typically you'll see a glycol, so I'll probably use ethylene glycol for the example of this. So hydrazine, that's the first thing we have here. Hydrazine looks like this: NH2, H2. It is nucleophilic because we have the lone pair on the nitrogens there. It's going to come in, it's going to nucleophilically attack the carbonyl carbon. We're going to kick these electrons up onto our oxygen. Now for the intermediate, I'm going to show you this tetrahedral intermediate. I'm going to abbreviate. The aromatic ring is just pH, so I can save some space. So we have, like I said, our tetrahedral intermediate here. Negative charge on our oxygen. 1, 2, 3, yep. And now we have NH2 plus and we have NH2. Now there's going to be a proton transfer step where you can functionally think of it as the oxygen steals the proton off that amine that has the positive charge of the nitrogen. Not really amine anymore. This is similar to the reaction mechanism for imine formation. Then we have this intermediate right here. We have our lone pair back. Now, there's another proton transfer step. I see this described a couple different ways. Sometimes it gets a little hand wavy. But functionally, again, what we're doing is we're going to steal this proton. We're going to form a better leaving group. We're going to leave. So this is essentially just water now, H2O. We're going to donate these electrons here. Or sometimes you see them donated back to the nitrogen, and then these lone pairs was donated to form this double bond. Do whatever your professor wants to get full credit. And then we have this right here, and it looks like an imine, and it's because it basically isn't an imine, except it's a special type called a hydrozone. And this is the first intermediate we get after that first step, okay? So we get this hydrozone intermediate after our hydrazine step. Now I'm going to erase some of this to make more room for us. But remember that hydrozone. Now, we hit it with strong base and a high boiling point solvent. We have our hydrozone right here. Okay, NH2, yeah. Now we have a strong base. I'm using just hydroxide here. We are going to steal one of the protons from this nitrogen right here. Okay, so I'm going to actually make this NH. There we go. Bond, steal that. We're going to donate these electrons into this bond, but that's going to leave too many things on our nitrogen. Remember, we have a lone pair there still. So we're going to donate these down and have a negative charge here. And we're left with this. Oh, I'm sorry. There's a single bond there. I just drew this. Haha. That is not the correct molecular geometry. That's not an N either. Now we have our negative charge here, these electrons, and what that's going to do is grab a proton from our proton source, which would be our solvent in this case. We're going to say it's ethylene glycol. So we're going to grab that proton. We're going to jump those electrons up onto that oxygen. That's not so much important about the solvent. Just know that the solvent is a proton source. Sometimes you'll see it with water as well, but usually it's a higher boiling point solvent. So then we have this product right here. And essentially this just happens again. We have hydroxide come and steal this proton. Abstracted proton is the more correct term. I like to say steal. I anthropomorphize my chemistry a lot. Now we're going to kick these electrons down here to make our triple bond, but then we got to lose this bond right here. So we're going to kick those electrons down. And what we do is we'd form the negative charge there again. And we take another proton from our solvent source. So let's see if I can fit this in one. So because we just lost nitrogen gas here. So P, I don't know why I keep making an R. H. Take another ethylene glycol. Where we, and this is what is our final product right there. Now I know that's a lot of moving pieces, and that's okay. Depending on your professor, they might not want you to know all that, and they might just want you to know what the reaction does. Okay, so what it is it reduces ketones and aldehydes down to alkanes, and where it's really useful is for aryl ketones, like to get the n-alkylated benzene. Now this is under pretty strong basic conditions, so if you have a functional group on there or just some other part of the molecule that won't tolerate like strong base very well, this isn't going to be the way to go for you, okay? Because it's not going to tolerate that. Because just because we want it to do this doesn't mean this hydrazine might not start wreaking havoc somewhere else on your molecule, depending on how complex it is. So if you have something that is more tolerable of acids, you say you can use the Clemmensen reduction because it uses strong acid, and then vice versa.